Solving logarithmic equations. To solve a logarithmic equation, it needs to be written in one of the following forms. Log base b of a equals c. Once the equation is in this form, you may need to convert to exponential form. In this form, we have log base b of a equals log base b of c. Once the equation is in this form, a and c must be equal. Therefore, you may remove the logarithms and solve. Since logarithms and exponents are inverses, log base b of b to the u power equals u. Taking the logarithm of base b undoes raising b to a power in the same way that subtracting undoes adding or dividing undoes multiplying. The above would be read as, what number would you raise b to in order to get b to the u? By definition, the answer is u. We will use this to solve equations with exponents. This also works when raising a base b to the logarithm with the same base of a number. b raised to the power of log base b of u equals u. Raising b to log base b of u undoes the log base b function. This equation states, if I raise b to the number which I would need to raise b to get u, I will get u. We will also use this to solve equations with logarithms. Since the natural log and a power of e are inverses, the natural log of e to the x power equals x. Taking the natural log undoes raising e to a power. The above would be read, what number would you raise e to in order to get e to the x? By definition, the answer is x. This also works when raising e to the natural log of a number. E raised to the power of the natural log of x equals x. Raising e to the natural log of x undoes the natural log function. This equation states, if I raise e to the number which I would need to raise e to get x, I will get x. The above statement is confusing, but true. We will also use this to solve equations with natural logarithms. Solve the equation. Log of 3x plus 7 equals 2. Let's raise 10 to both sides of the equation to eliminate the log. Remember, if there's no base listed, it is base 10. So we're going to use the inverse property. 10 raised to the power of log base 10 of 3x plus 7, well, we can cancel these out, and we are left with just 3x plus 7 on the left side. On the right side, we have 10 squared, which is 100. Then we just solve for x, and we get x equals 31. Solve the equation. Log base 5 of 3x minus 14 equals 2, so we're going to solve for x. Let's raise 5 to both sides of the equation. Since this is log base 5, we can use the inverse property, and this cancels out with that, leaving us with 3x minus 14 on the left and 5 squared on the right. Then we just use algebra, solve x equals 13. Solve this equation for x. There are multiple ways to approach this question. Method 1. Rewrite in log form. So we have 3 to the x equals 10, which can be rewritten in this form. Log base 3 of 10 equals x. Then we can use the change of base formula. X equals the log of 10 over the log of 3, which you can do in a calculator. Method 2 says to take the log of both sides. Use the power rule of logs, so this exponent, the x, moves out front. We have x times log 3 equals log 10, and then we divide both sides by log 3, and we get the same thing we got up here, which we can use the calculator for and solve. It's about equal to 2.096. Solve. E to the 5x equals 4. We're going to take the natural log of both sides, and that will cancel out the natural log and the e and leave us with this 5x on the left. So 5x equals the natural log of 4. Divide both sides by 5, and then in your calculator you can put in the natural log of 4 divided by 5 and get approximately 0.0277. Solve. The natural log of 13x plus 5 equals 11. Since we're starting with the natural log, we will raise e to both sides of the equation, which will cancel out the natural log over here and leave us with 13x plus 5 on the left and e to the 11th power on the right. Then we can use some algebra, so subtract the 5, divide by 13. You can put this into your calculator, and we get that x is approximately equal to 4,605. Before we solve this equation, should we write this equation as a logarithm on one side or as a logarithm on both sides? We should write this equation as a single logarithm on one side using the rules of logs. We're going to contract it. Then we can solve the equation. Now solve the equation. We have log base 6 of x plus 2 plus log base 6 of 3 equals 2. So first we're going to change these into one term. So they're both log base 6 and they're added together. So we can change this to log base 6 of 3 times x plus 2. We're going to multiply that 3 to the x and the 2, so that becomes 3x plus 6. Then we're going to raise both sides of this equation, raise 6 to those powers so that we can undo that log function. That gives us 3x plus 6 equals 6 squared. So 3x plus 6 equals 36, 3x equals 30, x equals 10. Solve log base 9 of r plus 3 minus log base 9 of r equals log base 9 of r minus 1. First, we combine these into one term, so this becomes log base 9 of r plus 3 divided by r, since this is a negative sign. Now, both sides of the equation have log base 9, so we can set whatever's inside here equal to each other. So we can cancel out that log function. So we have r plus 3 over r equals r minus 1. Then we can go ahead and solve, so we can factor, and we get two solutions, r equals 3 or r equals negative 1. However, the solution negative 1 is extraneous, since you cannot take a log of m when m is less than or equal to 0. So we can't take a log of a negative number. Caution! Extraneous solutions. Remember, you cannot take a log of m when m is less than or equal to 0. Always check to see if your solution satisfies the original equation. Substitute the solutions r equals 3 and r equals negative 1 into the equation to check for extraneous solutions. R equals 3 yields a true equation, while r equals negative 1 yields the log of a negative number and is therefore extraneous. How can we use these concepts to solve this equation? 5 to the a squared power equals 60 to the a power. It is acceptable to take the log of both sides. You can then apply the properties of logarithms to solve. Now, let's solve the equation. We take the log of both sides, and then this exponent here is going to become a coefficient. So we bring that a squared down in front. We have a squared log 5. This a will also become a coefficient. So we have a times log 60. Then we can divide both sides by a, which leaves one a over here since this was a squared, but gets rid of that one entirely. So we have a times log 5 equals log 60. Divide both sides by log 5, and we get a equals log 60 over log 5, which is approximately equal to 2.544. Try solving for b. 4 to the b minus 2 power equals 27 to the b power. Method 1. We take the natural log of both sides. We bring the exponents down to become coefficients. We divide both sides by b. Then we divide both sides by the natural log of 4. So on this side, we're going to have the natural log of 27 divided by the natural log of 4, which is 2.377. Then we multiply both sides by b. And then we solve algebraically, and we get b equals negative 1.452. In method 2, we're going to take the log of both sides, bring the exponents down to become coefficients. We're going to multiply log 4 times b and negative 2. Then we're going to subtract b log 27 from both sides to get it on this side. And we're going to add 2 log 4 to both sides to get 2 log 4 over here. Now we're going to take out that b and bring it out front. And we have log 4 minus log 27. We're going to divide both sides by log 4 minus log 27. And we get this, which we can put into a calculator, and we get the same result, negative 1.452.